Today we're going to be talking about VSEPR theory and how to use molecular geometry to determine molecular dipoles and whether compounds can be polar or nonpolar based on their shape. So if you're not familiar with VSEPR theory, it stands for valence shell, electron pair, repulsion. So then, the way that these valence electrons are positioned around the center atom in a molecule, there will be repulsion because of the negatively charged electrons, and you're going to get a shape because of it, a three-dimensional shape. And so we have these larger categories for VSEPR based on the number of electron pair domains or the regions of electron density. That is how we're going to be able to determine the shape. And then we're going to be able to use electronegativity to determine the polarity of individual bonds. And then that's going to bring us to our dipole arrows and how our dipole arrows can help us predict the overall polarity of a molecule. The first example we're going to look at is going to be CO2. When we draw just a Lewis structure, we know carbon is going to be our center atom, and it's going to have double bonds to each of the oxygens. Now, counting up those regions of electron densities, there's the two regions around carbon, and then so that gives us our linear shape. Now, using the electronegativity of each of these atoms, each of these elements, carbon has an electronegativity of 2.55, while each of the oxygen is going to have an electronegativity of 3.44. When we take the difference between these electronegativity values, for each carbon-oxygen bond, the electronegativity difference is going to be 0.89. And so that is enough to be a polar bond. So then we would say, okay, well, the carbon-oxygen bond is polar, so we would assume that carbon dioxide overall is polar. That is why we're now having to consider the molecular geometry to actually see, is that true or not? So we're going to use our dipole arrows to start drawing where these shared electrons are going to be, right? Because we know if it's a polar bond, it's going to be unequal sharing. And so our dipole arrows will show us, well, where are they being pulled? Because oxygen is the more electronegative element, the shared electrons will be closer to each of the oxygen atoms. And so our dipole arrow is going to show that they will be pulled closer to the oxygen. Now, these are the same bonds on either side of carbon, right? You have the double bonded oxygen on the right, and then we also have the double bonded oxygen on the left. And so we can think about these as being equal magnitudes in opposite directions. So remember, the difference was about 0.89 in each direction. And so if they're going in exactly opposite directions, because this is a linear shape, we know that they will cancel each other out. So even though the individual carbon-oxygen bond is polar, these dipole arrows show us that they're not going to be polar overall, right? So CO2 is going to be a non-polar molecule because the canceling of these individual dipoles. Let's take a look at another example. So then for this next example, we're going to take a look at dichlorocarbene. Now, if we count the region of electrons around our center atom, we're going to get 3. But because one of these regions is a lone pair, it's not just going to be trigonal planar, it's going to be bent trigonal planar. From the previous example with CO2, we want to try to represent the dipole arrows in a very similar manner. But before we represent the dipole arrows, we have to determine the individual bond polarity. So reusing that electronegativity value from carbon, it is 2.55. And then now looking at the electronegativity of each chlorine, it's going to be 3.16. So the difference between these two atoms, carbon and chlorine, is going to give us an electronegativity difference of about 6.1. And that is enough to be polar, right? The polar bond is anything really above 0.4. And so, which one of these two elements is going to have the greater pull on the electrons? And so the greater negativity means that it'll have the stronger pull. And so when we draw our dipole arrows, that means that these shared electrons will be closer to each of the chlorines. The head of the arrows are going to show where the electrons are being pulled. So that's why we're drawing the head of the arrows towards the chlorine atoms. And so now that we know that our structure is bent trigonal planar, do these dipole arrows cancel out in exactly opposite directions? Now, they're both diagonal and they're both facing down, so I would not say that they cancel out the same way we saw the bond dipoles canceling in carbon dioxide. So this lone pair up top is going to force these two covalent bonds to push down, which then prevents them from being a complete symmetric shape. Because of that, we're actually going to have a net dipole. So our net dipole is actually going to be in the general direction of where the individual dipole arrows are being represented, right? So the chlorines are going to give us the more electronegative region, and then carbon is going to be the less electronegative region, so that we have a dipole overall going in the downward direction towards the more electronegative elements. So because of that, we would consider our compound here to be polar overall. So this is our first example of how we can use molecular geometry to determine the molecular polarity based off of bond dipoles. So if we look at beryllium dichloride, even though this is a metal bonded with nonmetals, this is going to be a covalent compound. And so we can think about shape first. Now there's two groups of electron dense regions around our center atom, around beryllium. And because it's only two regions, that is going to give us a linear shape. And then our next step is going to be using electronegativity to determine the polarity of each individual bond. So using the electronegativity values, beryllium has a value of 1.57, and then each chlorine has a value of 3.16. Now our difference for each of these bonds, because these bonds are the same, our difference is going to be 1.59. And so that is definitely a polar bond. So our next step is using our dipole arrows to represent the direction of the shared electrons. So more electronegative element has the stronger pull. So the chlorines are going to have the stronger pull compared to the beryllium atom. And so because these electronegativity differences are the same, right, we get the 1.59 on each side of the beryllium. So opposite directions with the same magnitude of electronegativity difference means that these dipole arrows cancel out. And so we're going to have a nonpolar molecule because of these canceling dipoles. Let's take a look at sulfur difluoride next. Sulfur is going to be our center atom with two pairs. And it's going to have a single covalent bond to each fluorine atom. Let's determine shape first. So we have 1, 2, 3, 4 regions of electrons around our center atom. So that is going to give us a tetrahedral shape. But then 2 of those 4 regions are specifically lone pairs. Because there are the 2 lone pairs, they're going to push the covalent bonds down, which give us a bent shape. And so we will have a bent tetrahedral molecular geometry. Using our periodic tables, we can say that the electronegativity of sulfur is 2.58, and my source comes from PubChem from NCBI, their periodic table on their website. It's a great resource. And then the electronegativity of fluorine is 3.98, and that goes for both of them. The difference between these electronegativities for each of these bonds, because these bonds are the same, is 1.4, which gives us polar bonds. Fluorine is more electronegative, so it is going to be better at pulling in those shared electrons. So that means that the arrows from our dipoles are going to be facing the fluorines. Now, the magnitude of the dipole is the same, right? Because the electronegativity is the same because they're identical bonds. But because we have a bent shape, these bonds are not facing opposite directions. Because they're not facing opposite directions, we cannot say that they cancel each other out. So because of that, we have a polar molecule overall. Our next example is going to be boron trifluoride. We have 3 regions of electrons around boron. Boron does not have a lone pair. And so the 3 electron domains, the 3 regions, tell us that this is going to be a trigonal planar shape. Now, the bond angles in a trigonal planar shape, for each of these bond angles, is 120 degrees. So this is a symmetric shape because it's cut into 3 pieces. When we think about the polarity overall, that is going to be very important. Let's first figure out what the individual bond polarity is. Boron has an electronegativity of 2.04, while the fluorines have electronegativity values of 3.98. When we find the difference in our electronegativity values, our difference is going to be 1.94. So each one of these bonds is very polar. And so we can draw our dipole arrows facing the electronegativity, or the atom with the greater electronegativity. Now, remember I said before, each one of these bond angles is 120 degrees. This is a symmetric shape. Because the bond dipoles are facing almost exactly, I should say exactly opposite directions. Because if they're all pulling on the boron with the same magnitude and all 3 of these directions have the same bond angle, shared electrons are all going to be pulled in equal and opposite directions from each other. So because of that, these bond dipoles will cancel each other out. All 3 of them will be canceled, which will then leave us with a nonpolar molecule overall. So when we talk about boron trifluoride, it is considered nonpolar because of its symmetric shape and the canceling of each individual bond dipole. Let's take a look at xenon tetrafluoride. Xenon tetrafluoride has 2 pairs while having 4 fluorine bonds. Now our wedges here in the front, they represent the fluorine atoms that are coming towards us. And then our dashes in the back, they represent the fluorines that are going away from us. So we use these wedges and dashes to help us represent 3-dimensional shapes or 3-dimensional directions while just having it as a 2-dimensional representation. Now, thinking about the shape here, we have 6 regions, 2 pairs, and 4 bonds. So our 6 regions tell us that this is going to be some type of octahedral shape. The 2 lone pairs are going to force these bonds to all be planar. They're all going to be on the same axes. So they're going to be almost like they're flat. So that is going to give us a square planar octahedral shape. Oh, I forgot to draw our lone pairs on all of our fluorine atoms. Let me not forget those. Fluorine's electronegativity value is going to be 3.98 consistently, right? The new element that we're looking at so far in this video is going to be xenon. Xenon has an electronegativity of 2.6. So when we talk about our electronegativity difference for all 4 of these bonds, right? Because all 4 bonds are the same, we get a 1.38 difference. So all of the individual xenon-fluorine bonds are considered polar because of this difference in electronegativity. So if we were to draw our dipole arrows would show that the more electronegative element is going to have the stronger pull. So all these shared electrons that xenon has are going to be pulled towards each of the individual fluorines. Now, we have to continue to think about bond angles here. Because xenon in this example gives us a square planar shape, all of the bond angles between each of the xenon-fluorine bonds are going to be 90 degrees. So all of these angles here, they're all going to be 90 degrees. So it's almost like they create this perfect square, hence our shape of square planar. Now, all of these dipoles are facing in opposite directions, right? It's almost like 4 corners of a square. Because they're being pulled all away from the xenon, all of these dipoles are going to cancel out. It's very similar to when we were looking at boron trifluoride, where it was a symmetric shape and the 120 degree angles canceled all of the bonds out. Whenever you have symmetric bonds with the same electronegativity differences, all of those individual bond dipoles will cancel. And so even though we have these lone pairs on the xenon, it is still going to be a non-polar molecule. So we have a lot going on here. But if we take it step by step, determining the shape, determining the individual bond polarity, and then thinking about our bond angles and the way that these bonds are actually represented in 3-dimensional space, we can then put all of this information together to predict if the bond dipoles are actually there or if they end up canceling each other out. And this is one of those examples where we do see them all canceling out because of their symmetric shape, because of the symmetric structure. Well, what happens if we have an example where we don't have a completely symmetric shape? So let's say we have boron again with 2 fluorines coming off, but instead of a third fluorine, we have a hydrogen. We have the 3 regions of electrons around boron here, and so it is going to be trigonal planar. And trigonal planar gives us bond angles of 120 degrees, right? So we were saying that it's symmetric because of these perfect 120 degree angles. But it's not completely symmetric like we saw in our previous example because we no longer have 3 fluorines, where we now replace one of them with a hydrogen atom. Boron's going to have electronegativity of 2.04. Each of the fluorines is going to be 3.98. Hydrogen is going to be 2.2. So we have 2 different types of bonds here. We have the boron-fluorine bond, and we also have the boron-hydrogen bond. Now, the difference in electronegativity for the boron-fluorine bond is 1.94. The electronegativity difference for the boron hydrogen bond is going to be 0.16. The boron fluorine bonds are polar, right? Because of their large difference in electronegativity. But the 0.16 for the boron hydrogen bond is below our threshold. It is smaller than 0.4. So this bond is actually just going to be nonpolar. So there is going to be no dipole for the boron hydrogen bond because those electrons will be shared equally. But we are able to draw the dipole arrows for both of the boron fluorine bonds. Both of these bonds have the same difference in electronegativity, while the boron hydrogen bond is the odd one out. Now, if we think about symmetry and we think about the way that dipoles cancel, do you think that these dipoles will be able to cancel each other out? It's because of this hydrogen here that does not provide us with a completely symmetric shape. So there is no dipole going in the upward direction, going away from both of the fluorine dipoles. And so we are going to be overall polar for this example because the dipoles go in the direction towards the fluorine atoms. So we get a net dipole facing both of the fluorines. So our next example here is CH3Cl. If we count the number of electron-dense regions, the number of electron domains, that gives us 4. We don't have any lone pairs around the carbon, so we're not going to have any pushing or repulsion of these bonds to give a different molecular geometry. It's just going to be tetrahedral. We have 2 different types of bonds here. We have the carbon-chlorine bond, and then we also have the carbon-hydrogen bonds. Chlorine has an electronegativity of 3.16. Carbon's electronegativity is 2.55. Each of the hydrogens has an electronegativity of 2.2. So our electronegativity difference for the carbon-chlorine bond is going to be 0.61. And then our electronegativity difference for the carbon-hydrogen bond is going to be 0.35. For carbon-chlorine, that is going to be a polar bond. For carbon-hydrogen, that is going to be a nonpolar bond. So when we think about our dipoles and we think about where these electrons are going to be pulled, the only one that's going to have an unequal sharing is the carbon-chlorine bond. Chlorine is more electronegative, so it'll have the stronger pull on the electrons. Because all of these carbon-hydrogen bonds are nonpolar, they are not going to have dipoles. All their electrons will be shared equally. So when we think about a net dipole for our shape here, it's going to be in the direction of chlorine because chlorine has the greater net electronegativity compared to carbon. And so we don't have anything canceling out that single dipole arrow, so we have a polar molecule overall. So our next example, we have phosphorus pentafluoride, PF5. We have 5 groups around phosphorus. Phosphorus does not have a lone pair here. So because of those 5 groups, our molecular geometry is going to be trigonal bipyramidal. There are 2 bond angles in trigonal bipyramidal. We have 90-degree bond angles, and then we also have 120-degree bond angles. The 120-degree bond angles are between the 3 fluorines that are planar here. We have the fluorine going up and the fluorine going down. Those are both moving in the y-axis, while the 3 that are here are all in the same y value. So they're all basically flat. And so we can think about it being almost like trigonal planar, and that is what gives us the 120-degree bond angle. However, when we start comparing our other ones, when we start comparing the fluorine up top and the fluorine on the bottom, the ones that have the positive and negative y values for their y axes, that is where we start to see our 90-degree bond angle. Because if this is on our y-axis of 0, and then let's say that this is now having a positive y value, this angle here between these, this is going to be a 90-degree angle. It's almost like a right angle because one goes out and then one goes straight up. And then so that is how we get our 90-degree bond angle for that bond. So that is how we're able to have these two different bond angles. When we think about the individual electronegativity to start to determine bond polarity, each of the fluorines is going to be 3.98, while our phosphorus is going to be 2.19. So then our electronegativity difference between these two is going to be 1.79, which gives us a very polar bond. So all of these phosphorus-fluorine bonds are going to be polar, which gives us unequal sharing, where each one of these fluorines is going to have the stronger pull on the electrons. Now, do you think these will cancel out? Do you think that this shape is symmetric so that all of the dipoles will cancel out, or will we have any lingering dipoles that'll make our molecule polar? Remember what I was saying before about our bond angles, right? Each of the 120-degree bond angles is symmetric, right? So all three of these phosphorus atoms, the ones that are on our y value of 0, they all have a symmetric arrangement around phosphorus. So all of these dipoles here, those three will end up canceling each other out because they have that symmetric angle of 120 degrees. That leaves the two fluorines in the positive and the negative y-axis. They have the same x value and the same z value. It's just that one is going up and one's going down. That will allow us to cancel out these two dipoles as well. That leaves us with a net dipole of 0. All 5 of these will cancel out. The 3 in the middle will cancel each other out, while the one on top and the one on bottom cancel each other out. So it's not like all 5 cancel each other out at the same time. It's looking at it from different angles. And so considering these different perspectives, these different arrangements of these phosphorus-fluorine bonds, that is what allows us to determine that we have a nonpolar molecule overall. Our next example is ClF3, chlorine trifluoride. We have 5 regions of electrons around chlorine here, which is our center atom. So that is going to give us a trigonal pyramidal shape. Trigonal bipyramidal. But because 2 of those 5 groups are lone pairs, that is going to push some of these bonds down. So we actually end up with a T-shape trigonal bipyramidal molecular geometry. Now, all 3 of these fluorine-chlorine bonds, they are going to be planar, which is why we don't see any of them on wedges and any of them on dashes. So we can think about the bond angle between these two being 90 degrees, the same as this one, also being 90 degrees. But then there's this angle, which is 180 degrees, which gives us a T shape. It's almost just shaped like a T, where you have the fluorines on opposing sides and then the fluorine that's on the bottom. So what do you think? Do you think that we are going to have a polar or nonpolar molecule? So the chlorine-fluorine bond is going to be a polar bond. That is because our difference in electronegativity of chlorine being 3.16 and fluorine being 3.98 gives us 0.82, which is polar, right? So when we draw our dipole arrows, each one of these fluorines is going to have the stronger pull on electrons. So then remember what I was saying before about these bond angles. We don't have a completely symmetric shape here. Two of these bond angles are 90 degrees, but then we have the 180 degrees between these two fluorines here. So thinking about equal and opposite directions, these fluorine bonds that are here, these dipoles will cancel each other out because they're equal and opposite. But this one fluorine down here, the bottom of our T, there's nothing up top that will cancel it out in terms of a bond dipole. So it is the only remaining dipole, which means that this indeed will be a polar molecule. For our last example, we're going to look at iodine pentafluoride. Iodine, in this example, has 6 regions of electrons, 5 bonds, and 1 pair. Because of that 1 pair, it is going to force our octahedral shape to specifically be square pyramidal. Square pyramidal has 2 bond angles. Between all of these fluorines here that are planar, that gives us a square shape. What do you think that their bond angle is going to be if it's a square shape? It's going to be 90 degrees. All of those ones are 90 degrees. That leaves this fluorine that's on the bottom. That's in our negative y-axis. Forgot to draw those lone pairs on fluorine again. That lone pair that's up top is going to push those 4 planar fluorine bonds down. Because of that, these bond angles between the fluorine and the negative y-axis are all going to be a little bit less than 90 degrees. So that is why we have these 2 different bond angles here. When we think about the individual iodine fluorine bond and its electronegativity difference, iodine has an electronegativity of 2.66, fluorine is 3.98. That gives us 1.32, which is a polar bond. So all of these fluorine iodine bonds are going to be polar, which means they're all going to have individual bond dipoles. Fluorine is more electronegative, so these bond dipoles will be facing the fluorines. And then we also have this 5th one down here. Now, remember what we think about with symmetric structures. The 4 fluorines that are on the sides, on the dashes and the wedges, those are square. They have bond angles of 90 degrees. Because of that, they are going to cancel each other out. So we will no longer have these individual dipoles for the square-shaped fluorines in our shape here. That only leaves the fluorine that, in this perspective, in the negative y-axis, the one that is going down. So because that is the only remaining dipole, there's nothing up top to cancel it. That is going to make our molecule polar overall.